Welcome back, everybody. So this is the first video lecture on reactive transport. So this is the fourth topic in this contamination, groundwater contamination course. And now we're really getting into reactive transport, meaning, things that are moving in the aquifer and that react with the environment. So maybe mass is disappearing, maybe there's some biological reactions, biological uptake, for example, or growth. So anyways, things change as they move, okay? And so this, in this very first lecture, right, we'll describe the impact of sorption especially. And sorption, again, is the reaction of molecules on surfaces, essentially. So they attach to surfaces. So of course, water in porous media underground, water is moving through mineral surfaces, right? That's the very definition, if you will, of the porous media underground. And so anything that is charged or that is, able to interact with those surfaces, with those mineral surfaces, may experience some sorption and then desorption later on. Similarly, in organic porous media, so porous media that has a lot of organic content, right? If you are a molecule that has some hydrophobic properties or affinity to organic matter, then same thing. You could be absorbed into the organic matter and then desorbed at a later time, and your transport behavior will be different from the water moving through. So here's an example of retardation, where we can see benzene here. So water is here, the very first elution or the very first breakthrough curve, right? And then you can see that different organic compound come out of the aquifer or out of the column, out of the porous media at later times, essentially. So they've been retained in the matrix, and that's what we call, that's because of the process of sorption, and that causes what we call a retardation factor. Now, other principles are biodegradation, radioactive decay, that precipitation also can actually reduce concentration or reduce, the amount of matter in transport, and we'll see those in different lectures. Okay, so for the sorption reaction, and again, these lectures are going to be quite a bit, on the chemistry side, and I very highly recommend the Stum and Morgan, Stum, I believe, double M, and Morgan book, if you're interested in that aspect of, transport and contamination, aquatic chemistry, essentially. I think the Stum and Morgan is actually called aquatic chemistry. So, entire courses are taught on aquatic chemistry, and this is a whole topic in and of itself. Here we can but, scrape the surface of such advanced topics. But I'm trying to introduce, the main topics that are relevant for transport in groundwater. Okay, so the reaction that we're looking at here is some sort of sorbing species S that comes into contact with a surface X, right, or an adsorbate. And they combine to form a complex SX, right? So the sorbing species is on the surface and retained on the surface as SX. Now, one thing that will be a common thread through these upcoming few lectures is that the transport equation, which is here the advection and dispersion equation, right? So the advection here, dispersion here, right, is modified, if you will, with an added term, which can be a source or sink term, which can be, in this case, for the sorption, right, the change in the sorbing concentration, which I'll describe in a second, anything else, but that's basically a reactive advection dispersion equation, RAD. So it's a reactive advection dispersion equation, essentially, where the reactive part can be, again, for sorption, I'll describe in a second, but, you'll see that we add a term, basically, for also biological reactions, for deposition, resuspension, for example, etc., etc. Even like nonlinear models that we'll see, like transient storage models, for example, we just add a term basically to the advection dispersion equation. So, the very basic level, that's really what we're doing. Here, if we look specifically at sorption, what we're looking at here is the change in the sorbed concentration, right? So S, again, is the sorbing species, the species that gets attached, and that's the concentration we want to track, right? We want to know like how much of this species is on surfaces now, and that's S. Now note that S has different units from C, right? When that thing is in solution, the concentration is in mass per volume typically, where in 1D that can be mass per length, but think of it as milligrams per liter, right? Or moles per liter if we're talking in moles. When you're sorbed, now you're not per liter, you're like per, per surface area, or what is it exactly? So typically what we do is mass per mass actually. So it's a mass of sorbed, species per mass of matrix, per mass of mineral matrix, or mineral or organic, or whatever the matrix is. But it's a mass per mass, it's a percent, if you will. So notice that if this has no units, essentially, if it's mass per mass, then, the units don't check with dc dt, right? This is mass per volume per time. So now we need the per volume here, right? So notice that this is the mass per volume, the density, right? The density rho is a mass per volume. So now we're recovering these units, and also notice how we have theta, which here is the porosity, right? So now the problem is, right, porosity intervenes here because we don't have a strict equivalence, because now we're absorbing on the surface of, the volume of water to the volume of media, right, is different. So that's where you have the porosity sort of, transforming those volumes between just the whole media versus the pore volume. Okay. And now we've recovered the units, the proper units. Now this term here, we can describe here from the chain rule, right? We can just write that ds dt is ds dc dc dt, right? And notice how now we are recovering what we're looking for, which is a change in concentration in the dissolved form, right? So again, this is just the chain rule. So this is true for any, you can put x here, you can put any variable, that will always be true. That's just the chain rule. But the advantage is that now we have dc dt here, so we can write this term in terms of dc dt, and now factor, put in the equation and find a relationship with the dissolved species. Now if we plug this back in, right, we end up with rho over theta ds dc times dc dt. Now here, if we plug this back in, notice that I'm switching everything to the left-hand side. So 1 is for this term here, right? The 1 here corresponds to this term here. And then the rho over theta kappa corresponds to rho over theta ds dc. So meaning kp equals ds dc. This is really important. So this is a partition coefficient, we call it. And notice that this gives us a relationship between the sorb concentration, the amount of a species that is sorbed onto surfaces, and the amount of that same species that is dissolved in solution, right? So we assume that there's a constant in this case, and we'll describe that in a second. But there's a partition coefficient that says, hey, X amount or X percent of that dissolved stuff is going to get, sorbed onto surfaces. That's really how that works. Okay, so again, here dc dt, here is partition coefficient, and then rho over theta is there. And notice that now we have a term here that just a factor of dc dt that we can call a retardation factor. Again, so long as k is a constant, so ds dc is a constant. If this is a constant, right, now we have a unique retardation factor that's just a number, essentially, right, that tells you how much that species is retarded during transport. Okay, so this is our equation now that we're using for retardation. And notice how all it's doing, basically, so we have the exact same equation, transport equation, as we had before, the advection dispersion equation, except now we have that retardation factor up front. And the only difference, so notice how those things are exactly the same, they're just slower, essentially. So another way to think about it, right, is that our advection dispersion equation is modified, again, if this is a constant, right, you can think of it as the dispersion is modified by, instead of d, now we have d over r, right, and instead of u, we have u over r, so the velocity is much lower, right, and the dispersion coefficient is smaller, so everything is just like slowed down, basically. It's the exact same transport, except water is faster, and now that stuff is retarded, to some amount. Again, if R is more than 1. If R is less than 1, right, then this would be the opposite, so it's accelerated, right? So typically R is always more than 1, meaning, there's actual retardation, not acceleration. And again, this is all assuming that the partition coefficient here is called KD, KP, same thing. It's assuming that the amount absorbed and the amount in solution, there's a constant relationship between those things, right? What we call linear sorption. Now in reality, a lot of times, the sorption is not linear. Again, here, notice how the velocity and the dispersion coefficient are simply the same divided by R, and that's it. Very simple transport mechanism. Again, the same illustration as we had before, and you can see the water is just the fastest. These are for, as a function of distance, right? So water is in front, and then everything that is retarded is behind it, basically in the column, in the transport column. Same thing here, same concept, right? Something is faster, and then the retarded species is in the back. Now, a lot of times, things are not so nice, and we get retardation that is not linear, meaning, right? Meaning that the amount absorbed and the amount in solution is not constant, or in other words, the amount absorbed to surfaces depends on the amount in solution. So now we have a nonlinear relationship between, again, the amount on surfaces and the amount in solution. So things get a little tricky. So this number here is not a constant anymore. And you can see that if we replace the partition coefficient from a constant to some expression, which is a function of C, now we can carry this inside, but now we have very nonlinear equations, essentially, where concentration now is also in the retardation factor. So things are very much more complicated. And that leads to behaviors that are also interesting, because now we can see that there's some added tailing here. You can see in that graph here, that curve, that now it's not just retarded, meaning it's not just that things are shifted in time, but now they're also shifted in shapes, right? Because now imagine you're sitting on the surface of a grain, right? Let's say a sand grain, you're a molecule there sitting there, and there's a plume of a pollution or a absorbing, compound flowing by you. At the peak of the concentration, right? At the peak concentration, there's a lot of stuff in the water, so it would make sense that there's a lot of stuff that gets stuck on the mineral, near you. But at some point, if everything is, all the sites, the sorption sites around you are taken, it doesn't matter how much there's in solution, right? Because there's only so much absorbing site. So it makes sense that it's not just a percent of whatever is flowing by that is getting stuck, but it's also a function of, the amount of sorption sites available or behavior. And then once everything is gone, right, there's very little, when you're in the tail, there's very little mass or very few particles, molecules flowing in the flow, but now you have a lot of neighbors, attached, so it would make sense now that all of that stuff is coming back out, right, is desorbing, because there's basically clean water and, concentration gradients, right, you're moving against them, so you're just like desorbing and going back in the flow. So now again, it's not directly proportional to what's in the flow, like there's much more desorption now that the water is clean. So there's a non-linear, and that's why you have those tailing, right? This tailing behavior here is that later part when, you have essentially clean water above you, and now you have a lot of particles stuck on surfaces that desorb, and so that's why you're retaining, non-linearly through time, and you have this tailing. Notice that this tailing, I'll talk about it again later towards the end of that fourth topic here, when we do those transient storage models. So transient storage models are able to capture those added tailing due to retardation or anything else, actually, and I'll talk about other processes that lead to tailing. Now there's other complications, around the topic of sorption. One of them is these two-surface sorption isotherms. So imagine that now you have a heterogeneous compound or heterogeneous media, right, where you have two types of surfaces, let's say, and you have different affinities for those two types of surfaces. So it could be, let's say, two types of minerals, or maybe you have minerals and organic surfaces, and you have two different types of affinities for those, right? Now you can have different Kp. So see what I mean? Like the K, the partition coefficient is still a constant, but only over some range of concentration. So that's one, complication. Another complication is organic compounds, and I'll talk very little about them. I mean, I'll talk about them because they're really important for water pollution. Let's say gasoline is an organic compound, right? All those benzene, trichloroethylene, many of these cleaning compounds that end up, polluting the environment are organic compounds. So it's quite important to understand, the partition of organics is different from other types of molecules. But the problem is, again, they're hydrophobic now, so they tend to leave the water just because they're hydrophobic. So again, their behavior is quite a bit more complicated, and now you have to think of a partition coefficient between the water, the liquid phase, the hydrophilic, the water phase, and the hydrophobic compound. So there's a repulsion between them that makes their behavior, the transport, even more complicated. Other complication of nonlinear sorption, you can see here, and this is going back to the tailing problem, right? This is a breakthrough curve, so this is time here, concentration versus time, and you're sitting at a station, you're sitting in the aquifer somewhere, you have a well, and you're sampling that well over time, and there's a plume going back, so there's a maximum and a minimum, and notice here the log-log scale, right? So we're looking at, the data in the log-log plot. So these straight lines here are Paolo behavior, essentially. So it's, what that means is that there's always a little bit remaining, right? So there's this complicated tailing behavior, basically, at late times where there's always some mass. It seems that there's always some mass sort of coming out of these aquifers, over time, even when the cleanup is done, essentially. So again, and that can be, physical, or that can be chemical, through sorption. So the tailing behavior, again, we'll go back to that when we look at transient storage models and how we can account for those in modeling. Okay, so in conclusion, right, water flowing in aquifers, carries a lot of solutes with it, and those things that it carries with it may or may not behave like water, right? So when there is reactive transport, so let's say sorption, things can be retarded in the transport, so water is going to go in front, and then things are going to come out later. Essentially, that's really the effect of sorption. Here is an example of oxidoreduction chains, right? Where you can see that near here we have methanogenesis. So that's like the, methane is that flammable gas that you may smell in a swamp, for example, that has very little oxygen in it. And you have a whole cascade of reaction up to, the oxic reactions on the outer flow. And this is also quite typical of groundwater because groundwater is sequestrated from the atmosphere, essentially. So you have a lot of reduced species, right, flowing with the groundwater. And then when it comes back out and hit the air, you have this reaction with the oxygen in the air, right, these oxidoreduction reactions, which, again, I'm not going to go too much into, but this is very fascinating if you want to learn about, biology and oxidoreduction reactions. Again, I invite you to go check out the sum. But, just the broad brush here is that, oxygen is essentially, an atmospheric compound. Obviously, it's, present in the atmosphere. Underground, a lot of reactions actually strip the oxygen, and you have a lot of hypoxic reaction or reactions that don't need the oxygen. So all of those, right? So you use the oxygen that you can. So the next one is nitrate has some oxygen, so we use that. And then when we're done respiring nitrate, then we, the electron flows from different, other compounds, basically, all the way down to carbon dioxide and going into methanogenesis. When that water comes out of the aquifer, and comes into contact with the air, now there's more oxygen, and now you have oxygenation. So, for example, iron, we'll do an example with iron in a few lectures. When reduced iron hits the oxygen in the atmosphere, then it becomes oxygenated, right? So iron 3, and now we have literally rust, right? So this is rust that comes out of the ground, and you can see that when you walk around in the woods and you see like some groundwater seepage, you can see that it has that distinct, rust red color, or even in the, banks of rivers when you have groundwater seepage, you can see that red color of the rust, when it hits the atmosphere. Okay, I'll leave it there. Thank you very much. And in the next video, I will talk about biological reaction and first order, equilibrium, and then kinetics. Thank you.